Review questions, Electricity and Electronics, 10th edition by Gerrish and others. Chapter 2. All sections in review and test your knowledge questions are included. Content, of course, is by the authors of the textbook. Answers, narrations, and explanations by Hector Bello. Another name for a stationary magnet moving coil is the arson ball movement. Explain how a moving coil meter operates. When a current passes through a moving coil, a magnetic field is produced. This field reacts with the stationary field and causes rotation or deflection of the needle. Again, if you have to pause the video to answer the questions before they're shown, you can do that. You must be careful when handling a moving coil. Why? Because it could be damaged by impact. A linear meter scale has blank spaced marks to indicate circuit values. It has equally marked spaces. An ammeter is used to measure current. In order to measure higher current, a or an blank or alternate path is provided for current. Fill in the blank. A shunt is used to provide for an alternate path. An ammeter should always be connected in blank with load in series. An ohm meter is used to measure what? Resistance. An ohm meter uses a or an blank scale. Fill in the blank. A nonlinear scale. An ammeter uses a blank scale. Linear scale. Again, an ammeter measures amperage or current. Why must you calibrate a ohm meter before use? For accuracy. Find the value of the multiplier resistor Rm shown on the figure on the right side. It should read 50 volts across points A and B. For this problem, we use the formula R for resistance, M for multiplier, equals E over I, or E divided I. If this formula looks familiar, it's because it is familiar. It should be, at least. It is a form of the Ohm's law. So resistance multiplier equals, in this case, 49.9 over 0.001. Again, we put for the voltage 49.9. Why? Because there are 50 volts being read across points A and B. And since on a multiplier resistor, typically for a ohm meter, for a voltmeter, no more than 0.1 volt is required to deflect the needle, the movement, all the way to top off, or to all the way to the number 1, which is from 0 to 1, 0 to 10, 0 to 20. In this case, is 0 to 20, so it'd be topped off at 20, which is would be equivalent to the 200 mark. So you take off the 0.1 volt from 50 volts, which gives you 49.9. Remember, we're looking for the resistance of Rm, or resistor multiplier, shown in the figure. So for that, we use a form of the Ohm's formula, or Ohm's law equation. We substituted its values 49.9 again, divided by 0.001. And where the 0.001 comes from is the amount of, it doesn't tell you here, but it's the amount of current that requires full deflection. So you put that there in place of I current, divide that, you get 49,000 ohms for the resistor value. So a 49,000 ohm or 4K ohm resistor will give you a reading of 0 to 50 volts across points A and B. Again, if it's 50 volts, it'll give you a full deflection. If it's somewhere in between, it will give you less than full deflection. What does the abbreviation COM or COM stand for on a meter? What is its polarity? The common is what this COM means, and its polarity is negative. The common is more often used in AC circuits as opposed to DC circuits. What does DMM stand for? Digital multimeter. How should you connect an ammeter to a circuit? In series with a load, by first opening up or breaking up the circuit. Which of the three main types of meters should never be used when the circuit is energized? An ohm meter. What is an electrical schematic? A technical drawing or diagram showing parts of the circuit and how they connect to each other. How the circuit connects, or how each part of the circuit connects to each other. What are electrical symbols used for? To represent different circuit components and their functions. Name 3 typical electrical drawings and the use of each. The first is block diagram, which shows flow and how the overall system works. The second is elementary wiring diagram, which clearly expresses how the system works. And the third is wiring diagram, which is an aid to install or troubleshoot the system. The Arsenval movement measures blank and blank. Fill in the blank. It measures voltage and current. A or an blank is an alternate path supplied for measuring large current. I've seen this before, so you should know. It is a shunt. An ammeter movement has a moving coil resistance of 50 ohms and requires 0.001 amperes for full scale deflection. Compute the shunt values for the ammeter to read the following ranges: 0 to 1 milliamp, 0 to 10 milliamp, and 0 to 50 milliamp. First, find the voltage for full scale deflection. Since we have already the ohms available and the amperes required for full scale deflection, we can compute the voltage for full scale deflection using Ohm's law, which equals voltage equals to 0.001 times 50, which is 50 ohms, which is 0.05. Breaking down the different settings, 1 to 1 milliamp, the first set of answers. We set up a version of the Ohm's law equation as R resistance S1 equal to voltage over or divided current. RS1 is the resistor, the shunt resistor value, and we get 0.05 divided 0.001. Again, we get 0.001 from 1 milliamp from the setting that we want to solve for, in this case 0 to 1 milliamp. So resistor S1 equals to 50 ohms. And as we can see in the drawing, in the figure, since the meter coil has already a 50 ohm resistor, there is no need for the resistor at position RS1. That one will do just fine to get us what we need, which is a voltage measurement of, a amperage measurement of 0 to 1 milliamp. Next setting, we solve for resistor S2, which equals to voltage over current, or divided current, which, plugging in the values again, 0.05 for the voltage, divided 0.010, which again comes from your 10 milliamp setting, 0 to 10 milliamp, 0.010 amps, and that gives us 5 ohms. Solving for your third setting, 0 to 50 milliamps, RS3 equals to power over current, which we can plug in 0.05 again, divided by 0.100, which is the setting of, that should be 0.50. So 0.05 divided 0.050, which is 50 milliamps, 0.05 divided 0.050 amps equals 1 ohm. So the answer for the third setting, 0 to 50 milliamps, is 1 ohm resistor for position at RS3. In this problem, we compute the multiplier resistors for the voltmeter in figure shown to use the following ranges. Again, looking at the problem, we want to compute for multiplier resistors of a voltmeter. Very important to differentiate between an ammeter and a voltmeter when working out problems. Also notice the difference in the figures, the way the resistors are set up. They are starkly different between an ammeter and a voltmeter. The ranges that we're going to be solving for is 0 to 1 volt, 0 to 10 volts, and 0 to 100 volts. Some conditions. 1. The moving coil resistance is a 50 ohm resistor. 2. The meter allows only 0.001 amps or 1 milliamp full scale deflection. And 3. 0.05 volts is allowed across the meter, no more than that. We get 0.05 volts from 0.001 amps times 50 ohms, which equals to 0.05 volts. Solving for the first setting, 0 to 1 volts, for the voltmeter, we get what looks like a Ohm's equation in a different form, again with the resistor on the left side. Solving for the resistor, Rm1, which equals to voltage divided current. Again, this is the multiplier resistor for a voltmeter. So we get 0.95 divided by 0.001. 0.95, why? Because we need 0.05 volts is allowed through the meter, right? So if we want to get up to 1 volt, so 1 volt minus 0.05 equals to 0.95. So we want to allow only 1 volt, so we use 0.95 volts in this formula to get the size of resistor, Rm1. That's the size of resistor we want to basically resist 0.95 volts out of 1 volt and allow 0.05 volts through. So if we want to resist 0.95, we have to know what Rm1 is by using 0.95 as your voltage, and you divide 0.95 volts by 0.001 amps, which is the allowable amount of current. In this case, is given in condition number 2. Again, another explanation of 1 volt, we must resist 0.95 to meet condition 3. And that's where we come from with the 0.95 volts. Just a quick and easy way to understand that. So Rm1 equals to 950 when you divide that. And that is 950 ohms. Next setting, 0 to 10 volts. Resistor M2 equals to voltage over current. And in this case, the voltage is 9.95. Again, we want to allow 0.05 volts through, so 10 volts, which is the maximum in this setting. We take 0.05 away, we are left with 9.95. We divide that by 0.001, which is your maximum allowable current, and that gives us 9,950 ohms, or 9.95 k ohms. The third setting, 0 to 100 volts. For the meter, we want to find resistor M3, the value for it to give us what we want, which is a reading of 0 to 100 volts. We plug in 9.95 for voltage. Again, we want to allow 0.05 volts, the same as the other two settings, 0.05 volts. And if we take away 0.05 volts from 100, we're left with 99.95 volts. And you divide that by your maximum allowable current, 0.001 again. That gives us a resistance of 99,950 ohms, or 99.595 k ohms. 99.95 k ohms. A meter is used to measure the value of an unknown resistance, and that is called a Ohm meter. The symbol that on an ohm meter scale represents what? That is the infinity symbol, not the one from the car. It's the mathematical infinity symbol, and it's a representation of what in your ohm meter. Represents high resistance or infinite resistance. When reading an unknown voltage value, you should set your selector position to what? Again, your voltage is from a voltmeter. If you don't know what the value is, what you're reading, you should select it to the highest possible voltage range setting. When using the ammeter, you should connect it in what kind of way? With the load in series. You want to open up the circuit and basically insert the meter as part of the circuit, the ammeter. What type of meter must be zeroed out? The ohm meter. What is meant by loading the circuit? This term is a bit more loaded than it looks. A bit more involved, so I took the time to go ahead and try to understand it and to be able to explain it just a bit better. And it does take a few steps. However, they're not too complicated. However, there are a few steps that you may want to consider and perhaps practice to get a better idea of what loading the circuit is. But to define, loading the circuit is when a voltmeter is connected across a resistor. In parallel with it, it loads the circuit due to the shunt resistors in the meter, causing a shunting effect, in fact an error, in voltage drop across the resistor. So basically, testing a resistor of voltage drop, testing for a voltage drop across a resistor, which you have to connect your meter in parallel with the resistor, let's say on a 2 resistor circuit, as the example in figure 2-11, which I will include here as a diagram in this page. When you load the circuit with your meter by testing this 1 resistor out of 2, the shunting effect of your meter, basically the resistors in your meter, introduce an error in voltage drop across the resistor. That is, if your meter is not of high resolution or a very high quality, you can actually introduce an error reading that voltage drop, and it'll give you a voltage drop that is different from what you would get if you were to work the theoretical voltage drop, let's say with the Ohm's law equation. And to show you how that is worked out, how we find out about that and why this actually is, why this happened, we have to define again a few things. The effective resistance is the total resistance read by your meter, not necessarily the actual resistance of the resistor. It is the resistance read by your meter, whether it's in error or accurate. Your effective resistance in formula is R1, or resistor 1, added to your resistor multiplier, or the resistor from your meter, which is your reading, your resistance meter at your meter, your resistance reading at your meter, that is Rm. Add those two and then divide it by 2 as shown. So in this case we have a resistor 1 value of 10,000. If you look at the diagram, we have a Rm value of 10,000. That is your resistance reading at your meter of 10,000. However, we plug in different values. We plug in half of those. R1, resistor 1, and Rm values are decreased by half by the voltage divided you actually create when you plug in your meter leads into the circuit across your resistor 1. So you actually have to use half of the values of R1 and Rm as shown. Instead of 10,000, you put 5,000 ohms plus 5,000 ohms, again for R1 and Rm. You divide the total for that addition, which is 10,000, divided by 2, and you get 5,000 ohms. So with the meter connected, the total circuit resistance becomes R effective plus R2. Again, R effective, or resistance effective, is your combined meter plus resistor 1 divided 2 reading. So it's a composite resistance reading, and you add that to the second resistor, R2, which gives you your R total, your resistance total, which in this case is 5,000 ohms plus 10,000 ohms, which equals 15,000 ohms. So your resistance total is 15,000 ohms. Continuing on, to get your total current, if you haven't gone through this lesson yet, your total current is the same at any point in a series circuit. So we must get this value by again using Ohm's law version of it. Current total equals to voltage divided resistance total, or R total. So current total equals to 10, which is 10 volts. The 10 volts at your power source in this circuit. See figure 2-11. 10 volts divided 15,000 ohms. 15,000 again is your resistance total. So current total equals, when you divide, equals 0.00066 amps. So to get your voltage at your resistor number 1, or ER1, you get your resistance, your current total multiplied by resistance total. Again, Ohm's law. So that gives you 0.00066 multiplied by 5,000 ohms. Again, we're looking for the voltage drop at R1, resistor 1. And 0.00066 times 5,000 equals 3.5 volts. That is your voltage drop at resistor 1. And that is your actual voltage reading at your voltmeter at ER1 when you measure across it. And this is an erroneous reading. You should be 5 volts or somewhere near 5 volts because you have a 10,000 ohm resistor and you have 10 volts. So you should get 5 volts at each resistor. Again, power or voltage across a 2 resistor circuit in series should divide equally in the 2 resistors. You'll find out about this more later in later chapters, but that is how it works. And it should be 5 volts. That is what you need to know for now, mainly. But yet it reads 3.5 volts. And that again is because you are introducing a small margin of error when you plug in your meter across that resistor, your cheap meter. So to continue, we want to find out the resistance voltage drop, the resistor 2 voltage drop, which ER2 equals current total times resistance total. So the voltage drop at resistor 2 equals to 0.00066 times, that's 0.0066 amps times 10,000 ohms, which is the ohmage value at your resistor. And that gives you 6.6 volts, which is higher than expected. It should be 5 volts. But yet, using the amperage given by your formula up top, that gives you 6.6 volts. So there's a margin of error there slightly because of the meter that we're using. So if a better meter is used, say a 50,000 ohm sensitivity meter, let's see what that gives us. Let's use an example 2-12. Some definitions again, how we get effective resistance. Again, we get half of what it would be because of the voltage divider. So a 50k ohm resistor sensitivity for your meter is actually 25k ohms, as shown here. So your effective resistors or effective resistance is 15,000 ohms. With the meter connected, the total circuit resistance becomes R effective plus R2 to equal R total. And your resistance total would be 25,000 ohms in this case with 50k ohm sensitivity meter. And again, using Ohm's law, I'm just using the same exact formulas as last slide, and substituting the new value, 50k ohms, and working out the formulas from there. So with the new R total of 25,000, divide 10 by 25,000, which is 10 volts, divided 25,000 ohms. That gives me a total current of 0.0004 amps this time around. So to get the voltage drop at R1, resistor 1, plug in the values. As you can see, we get 6 volts. A little closer to 5 than before, but yet still we are over the mark. Resistor 2 would be, in this case, 4 volts. So we actually went over the mark and on the first resistor and under the mark in the second resistor by using a 50k ohm sensitivity meter. It's apparently too high. So if a better meter is used, let's say 20k ohm sensitivity, which is probably among the better ones out there. Use an example 2-12 again, going through the same steps. Again, we're using a 20k ohm, so that half of that is 10,000. Half of the resistor value is 5,000. At those, you get 15,000 divided to 7,500 ohms. With the meter connected, the total circuit resistance is as shown in the formula. In this case, 17,500 ohms. So using the total resistance and our voltage, which is 10 volts, we divide 10 volts by 17,500 ohms. We get 0.000571 amps. Using the formula for finding the voltage drop across R1, that's resistor 1, we get 4.29 volts at resistor 1. Very much closer to 5 than before, but not quite 5 volts. Resistor 2, we get again a bit closer, but not quite 5 volts. In this case, 5.71. So to find the perfect resistor sensitivity meter, we must keep looking. Let's say if I buy a better meter which uses 30k ohms, probably the top quality, 30k ohm sensitivity. We have 30k ohm, 15,000. We have R1, 5,000. Added 20,000 ohms divided to 10,000 ohms for effective resistance. So for the resistance total, add effective resistance plus resistor number 2. And we get 20 ohms for resistance total. We divide 10 volts by 20,000 ohms, which is your resistance total again, we get 0.0005 amps. So the voltage drop across R1 using 0.005 amps times 10,000 ohms equals exactly 5 volts. No error. Use the same current total, get the same result for the voltage drop across R2 resistor. So we seem to have found the perfect meter at 3000 ohms of resistive resolution. What is considered the highest harmless current value? That is no more than 5 milliamps or 0.005 amps. What does GFI mean in electrics? It means ground fault interrupter. It is a mechanism that provides protection against excessive fault currents. The way it works is when the coil in this mechanism detects higher than normal current on the hot wire, it triggers a relay contact to open the circuit and stop the current. What is commonly used, or what commonly causes the skin resistance of a person to drop to a lower value? Moisture, like sweat or water. What is CPR? It is cardiopulmonary resuscitation, and it requires up-to-date training to perform.